I think rather than sort of talk to you, I think this is an instance where a picture's worth 1,000 words. And here's the before picture of the way MathLink and JLink and the rest used to work. You could be in the Mathematica world. Here's our geek, and they're using the Mathematica front end, which is interacting with a notebook, and that the MathLink is talking to the kernel. And with a JLink, you could communicate with a Java runtime, and similarly, if you program things properly, the Java runtime could call on the kernel for services. So there's this world here, the sort of Mathematica world. But there's also the Java world, but that was a very simple world in which you would write your source code in Java, it would compile down to a Java class file, and then that could be imported into Mathematica via JLink and install Java. There are many good things about this, but the disadvantage of it is that oftentimes if you needed to get things done, you needed to actually program in Java. And many people find Java to be a rather ponderous and old-fashioned language. So the good news is that the picture is now more complicated and there are more opportunities. There are a number of languages that have been developed over the past 5 or 10 years which say, look, the Java virtual machine is actually a terrific piece of software. The problem is that the Java language that compiles to it is rather fussy and doesn't handle some things well. And so lots of people have developed alternative languages which compile down to Java class files. Amongst those that I took a look at were Scala, Clojure, and actually in more recent days I took a quick look at a very new language called Extend, which comes out of the Eclipse Foundation, the people who make Eclipse. All of those compile down to, one way or another, to Java class files. And so it occurred to me that it should be possible, in theory, to just use JLink to communicate with those Java class files, and so you could accomplish the same things that you might want to without having to encounter Java. But as I say in my little introduction, just because it should work doesn't really mean that it actually does work. And so what I want to talk about today is whether in fact it does work and what are some of the subtleties involved. Why should you care? For one thing, you should care because Mathematica is great and it does tons of things, but it still doesn't do everything in the world. And there are areas such as natural language processing or machine learning and probably many others that you know about that I don't, in which you still really want to often bring in Java libraries or have access to Java code. And of course, while you could access those in Java, there may be occasions in which you want a subclass or you want to do loops inside that you don't want to write in Mathematica because of the traffic back and forth. And so you want to be able to write something that compiles down to a Java code. Other advantages are some of these new languages handle concurrency better. Some of them, I think, have a cleaner syntax and are actually a little more Mathematica-like. And finally, you end up learning a fair amount about, I think, the way both Mathematica works and the way these other languages work. So that's the use case. Here is a little wordle of some of the many languages that are being written that compile to the JVM. So what I want to do in this talk is to take a look at 2 and probably about 2.1 languages that actually do this and see some of the subtleties involved. And I think I'll start with the perhaps the most straightforward, which is Scala. And Scala purports to sort of be Java on steroids, a modern Java that gets rid of a lot of the bulky syntax of Java, but that does many of the same things. And so we've got to do the same things on the Mathematica side that we do when we're running regular JLink, which is we have to call the JLink package. We have to install Java. You'll notice that because oftentimes I use large data files, I've got this reinstall where I'm going to increase my heap size, Java heap size, to 2 gigabytes. We can make sure that it succeeds. And so what else do we need? Well, one of the things that when you run Scala, Scala is going to produce its own collections and its own data sets. And when your Scala class file exports that back and outputs a Scala object, Mathematica's got to understand how to interpret that. And so one of the things you need to add to your class path and then import in is the Scala library. And that's true, I think, whenever you're using one of these alternative languages, is you've got to tell Mathematica, here's how to deal with Scala. And just that you can do that. All right, and then of course the other thing is I've got to tell Mathematica where my Scala class files are. These are Scala class files that I made by writing Scala code, and Mathematica better know where those are. All right, so here's some Scala code, what you can see is I've created an object, and all I'm doing here is testing out how various collections work and how Mathematica is going to recognize those. So I write that up, I say compile it, and it creates a class file within a project. I don't know if you can actually see this, but we've got my Eclipse workspace, and you don't have to do this in Eclipse. There are lots of other things, but I actually found Eclipse to be the best of the many alternatives. It's going to produce sort of this directory which has binaries, which has various projects that I worked on, and here's various classes that get produced. All right, so we've done that, and now comes the big test as to whether I can actually load in one of these classes that's been created. You have to trust me that I ran this downstairs in the basement before the talk just 20 minutes ago, and it all worked, and I'm not going to risk actually doing it live here unless I have to. But you're just going to trust me that I honestly did this just a few minutes ago but decided to avoid the Murphy's Law jinx here. So we load in the Java class. We can now instantiate an object using the Mathematica Java new command, and we can see, let's see if this actually works. We can see that there are various methods that this object has, and what sort of objects they are, so that, you know, in some sense, this is the key slide, because this slide shows that you can use a language other than Java to create a Java class file, and that Mathematica can, in fact, communicate it and interrogate it, discover its methods. So from here on in, we're into the subtleties, but the fundamental proof of concept is there, that it actually does work. All right. So we can do things like examine the collection types that it's putting out, and I've got lots of types that I'm exploring here, so that, for example, here we are looking at one of the collection types. I guess this is an array, and we can just say, give me this array, and it produces the array. Remember, I created an array back up here in my Scala code. There's my S array right there. And so we can get it back. We can create tuples in Scala. And my tuple had 6 members, and we can get each of those 6 members back. One subtlety is that Mathematica doesn't like function names with underscores, and so just as in Java you have to replace underscores with the letter U, you need to replace your underscore with the letter U. We can get maps back. That is, basically maps are what Mathematica would call rules. Left-hand side maps to the right-hand side. And I had 4 elements in my map, and we can get those map elements back. And so basically, the collection stuff all works. You have to do a little exploring to try and figure out what method within the Scala collection does what, but it all works. All right, so in addition to creating objects, which are basically creating static methods, you can also create classes in Scala. And in the spirit of the famous add to functions and other things that you always see that are very simple, I decided to see whether you could just do some simple functionality with using Scala. So there's our source code. We instantiate an object, You might see that it starts out, it creates an object which has a variable, it has a state which is 0, and we can increment that state and find out its current state. We can keep doubling that current state, and if we do that 8 times, 2 to the 8th is 256. And again, it all basically works, and it really, to the Mathematica side user, it doesn't look any different than using Java, I think, using JLink in Java. I think it's pretty much indistinguishable. What else? We can create static methods. And so that is, these are methods that don't have to be, you don't have to instantiate an object, you just get them by virtue of having the class. Those all work splendidly. And here's some things that aren't so easy to do, at least as far as I know, within Java, which is supposing you don't want you want to create an anonymous function, just like you have in Mathematica. Can you do that within Scala? And Scala, certainly with operating within Scala you can do it, but can you now take that back and use it within Mathematica? And the answer is yes, you can. This is an anonymous function object, and there are all sorts of obscure methods on this function object, most of which I have no clue what they do. But I figured, why not try the most basic thing first? Let's apply that function just like you would in Mathematica. And as it turns out, it works. Okay? So you can start to do interesting things now that you have anonymous functions. So some of you may, I just took the colats example because I think it's kind of cool. You can write Mathematica code that goes through this sequence of the colats conjecture and does it. So the question is, can you do that within Scala? And the answer, I hope, is yes. So we're now going to take the next step. We're going to, 200's an even number, and so we divide it in half. And now let's use our Scala side anonymous function and do a nest while list. And when we do that, we do see the colats conjecture. We can do computational shortcuts where we compose one of these Scala anonymous functions with another and create another anonymous function. And now we can do a shortcut where we're taking 2 steps at a time. Okay? But still, I haven't really fully leveraged what Scala can do, because each time I'm sort of coming back to Mathematica and letting Mathematica do the looping construct. So could we do that all within Scala? And it turns out you can write. Scala is very nice. It has lots of functional programming constructs, or ones that you can create, that work a lot like Mathematica. So what we're going to do is we're going to create one of those, and what we end up with is we end up with the colat sequence being produced all within Scala and simply exported back to Mathematica. So that's one of the nice things. One of the other things you always want to test is, okay, I can use Scala from within Mathematica. Can I use Mathematica from within Scala? And the answer is yes, you can. So here's the little piece of code that takes any arbitrary Mathematica expression that will resolve down to an integer and lets you run it. And so let's actually pray that this works. And it didn't. This one here? And look at, no. Let's just see if this works. Okay, so it did. It did an integral. Basically I said, Scala, please do an integral. Scala, of course, I think doesn't know how to do an integral, so it calls Mathematica for help, and we get it back within Mathematica. So there are things called traits in Scala that do multiple inheritance. And one of the other things you might want to be able to do is to call other Java side packages from within Scala. So could I write Scala code that calls other Java packages, does work, and then exports it all back to Mathematica? And my platform for testing this out was a very nice package called Weka, which does machine learning. And what I'm going to tell you is, because I want to get to Clojure, is that it all works. that you can have Scala code, call Java, get the result back into Scala, and have Mathematica slurp that up, so that now, if you want to write code that accesses one of these external libraries and, say, does looping over it, or does anonymous functions over various pieces of Java code, you are able to do it. And I'm going to leave it at that and move to Clojure. So let's look at Clojure. Okay. Clojure is a really interesting language. How many of you are familiar with it? Okay, so it's sort of modern Lisp, and because it's modern Lisp, I think it's actually much easier for Mathematica programmers to access it, because you're used to functional languages and the head comes first and then the other arguments follow. And that's the way Clojure works. And apparently this freaks people out who aren't used to functional languages, but I found it made total sense. And so again, what do we have to do to use it? We're going to have to tell Mathematica, the Mathematica side, hey, you need to understand Clojure. So you're going to have to get the Clojure jar file and put that on your class path and load it up. And you're going to have to tell Mathematica where your classes are that you've created as a result of running Clojure. That was an adventure. But let's look at some Clojure code. Here's some very simple Clojure code. We're going to declare a namespace, which is kind of like a package, and we're going to say, let's create a function. The function, I decided that we wouldn't use add2, we would use add3. And so we're going to say add3, it takes a single argument. You'll notice the argument isn't typed. That's because Clojure is not a strongly typed language. And that looks like Mathematica full form, doesn't it? Just the plus operator, we would say actually plus in Mathematica, x and 3, and if I could just sort of pencil in brackets there before the x and after the 3, you'd say that looks just like Mathematica. And so that's one of the very nice things, I think, about moving to Clojure from a Mathematica background. What it does, though, what's a little bit nasty, is that the file it the class it creates has this rather funny name, where it's going to take the package name here, Clojure.Mathematica core, and then it's going to create essentially, it's going to treat it as a private function. And it's going to stick a $sign, and then it's going to have I add 3. And so now what do we do with I add 3? Well, we have all these methods that we could use on it, and none of them seem to say straightforwardly, couldn't I just put a 6 after that, or an 8 after that? And you have to go through this intermediate step with Clojure of saying invoke. Just like with Scala, the magic word was apply. With Clojure, the magic word is invoke. And then you think, okay, well, if I put in 4, I should get out 7. But in fact, when you put in 4, it fails. Why does it fail? It fails because we need to look at the method signature of the invoke method. And what you're going to see is that the invoke method wants an object. It does not want an integer. It wants a Java-style object. And fortunately, we can be rescued here. Mathematica JLink has this thing called make Java object. And once we wrap that around it, it all works. Okay? But what you should be thinking is, what a pain in the butt. Okay? First, we've got to go through this step of invoke. Then we've got to convert things to Java objects. I'm never using Clojure. Okay? So, can we do better? And the answer is yes, we can. So, one of the things you can do is type hinting. You can tell Clojure, hey, return a double. Probably should have been an int, but whatever. Return a double and expect a double, and then do the same function. Okay? So you're giving it just some instructions to the compiler as to what you want. And now, if we look at this code, right. If we look at invoke, invoke still wants an object. But now we get the benefit, I'm going to take off eliminate inherited objects. So now we just look at the objects that this class itself produced. We get this new exciting method called invoke prim. And invoke prim lets me take a double. And so now I don't have to go through this hullabaloo of making a Java object. I can simply say invoke prim and 4, and now I add 4 plus 3, and I get 7. Okay? But you're still probably thinking, that's not really what I want to do. This whole invoke thing is awfully cluttering. And that's because, really, although this is all wrapped up in instantiation of classes, really I've got a static function that has nothing to do with classes. And so the question is, can we do yet better? And the answer is yes, we can. Okay? One of the things you can do is to give the Clojure compiler further instructions. Okay? And so you can see my function, I add double 3, and then we've got this other stuff, the static, I add double 3, takes a double, returns a double, and then we've got some aliasing down there. And if you go through all of that, you will in fact, at the end of the day, have something that is much nicer. You will have something that actually will work, and somehow the code that actually shows that is gone. All right, so again, you're going to have to, let's see if you are going to need to trust me, I think. You're going to need to trust me that when I load that Java class in now, I can now just use it like a regular JLink static function. I add double 3. If someone wants to see it afterwards, I will be happy to show it off. The answer is, with more work on the Clojure side, you can create things that work much more easily on the Mathematica side. Is this still a pain in the behind? And I would say yes, it is, to be honest. That is, I thought Clojure was a delightful language, and it's really elegant and pretty. Although it boasts of being able to be very interoperable with Java and to work with other Java classes and the like, what you actually need to do in its current incarnation to create a well-working Java class is a bit of a nuisance. Okay? But the rewards are that you do get anonymous functions, you do get Clojure collections to work very nicely, and Clojure has a very rich set of collections. Can you call Mathematica from inside Clojure? And the answer is that you can. There's the code that you need to tell Clojure, hey, call Mathematica and help. And what you can see is, let's see if I can actually get this to work. Okay, here's the piece of code I need. I'm going to launch this static method, and it has failed. I think that may be because I have too many kernels running it right now, because I've got too many people calling it. So you're going to again need to trust me that this actually works when I don't have multiple kernels running. Okay, what about a Java interoperability? Can I write code in Clojure that can then call things like my Java Weka classes? And so can I get my work done mostly in Clojure, calling stuff that someone else has written in Weka, but then spit the answer back into Mathematica, where I can have Mathematica do its thing and analyze the data and make nice graphics and do all the things that Mathematica is absolutely fantastic at and manipulates and all that stuff? And the answer is yes, you can. And here I'm basically taking one of these little files and actually going through the process of running a naive Bayes classifier on flower data and having it actually produce a report. So the short version on Clojure is a very elegant language. It still, I think, has some issues with making it convenient to produce the kind of Java classes that I think you would want to use. I have 1 minute left before the little yellow light goes off, and so I want to spend a second on extend. Extend I discovered about a week before the talk. I think it only was released in July, so I think I'm sort of forgiven. And the Extend it boasts of being sort of a little language that just fixes the worst things of Java, like its failure to make type inferences and its inability to handle lambda expressions. And I have to say, here's some code that's written in Extend, and it looks more Java-like certainly than Clojure. In some ways I think it looks more Java-like than stuff that's written in Scala. I will tell you that in terms of actually getting work done, easiest thing to use. This was easy. Learning curve, very shallow. It produces, what I like about Extend is that it cross-compiles. What it does is it produces Java source code, which then compiles down to Java class files, so that I can now go to someone who knows, if I've got an issue, I can go to someone who knows Java and they can tell me, hey, here's the problem with your code. Whereas, and the Java world's this huge world. It's always ranked as one of the top 2 or 3 languages in the world. Whereas Clojure is, language 50, and Scala is language 35, and finding someone who knows Scala is difficult. But finding someone who knows Java, that's easy. And so I think people ought to, and it was designed by Eclipse, so it runs beautifully in the Eclipse environment. And so here am I getting my work done. You can create lambda expressions, which are like anonymous functions. It does all sorts of things, including let you sing songs. So let me take some questions.